Hello, that was an easy fix, okay. So we all know that those sort of rocky world and temperate climate is not enough in and of itself for a planet to be habitable. If we want to form things like the organic biomolecules, like we have here on Earth, we need to inherit the precursors for this chemistry as well. And in the case of organic life on Earth, those precursors are the elements carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. So what we would really like to know is, do these rocky temperate planets also have the right inventories of these prebiotic building blocks such that life may actually develop? And unfortunately, we're still decades at the very least away from actually characterizing the volatile compositions on rocky worlds. So instead, what we can do is study the chemical environments that planets are forming in, and this gives us a real sense of both how planet formation takes place in the first place and also how planets are seeded with these biocritical ingredients. So when I talk about prebiotic building blocks, there's sort of two angles that you can think of this. The first is to try to understand the total inventory of biogenic elements that are contained within the gas and solids of planet-forming material. So just, is there enough of these elemental building blocks for volatile organic chemistry to proceed? The second angle is to consider what the form of these elements is. So are volatile elements processed into larger, maybe even organic molecules? And can you deliver this prebiotic feedstock intact to young planets, potentially allowing you to sort of jumpstart the chemistry more efficiently than if you just care about the elemental ingredients? So we don't yet know how life exactly originated on Earth, and so both of these angles are still really valuable, and so we'll sort of be drawing from both of them in this talk. All right, so how do we probe these really complex questions of chemistry of planet formation? We have a lot of different tools at our disposal. So this is a schematic that I've made to sort of outline the different pieces that we can use to approach this question. And I'm going to walk through this schematic now to sort of show what these different pieces mean. So the first thing to consider is that volatile elements can occur either in the gas phase or the solid phase in star and planet forming regions. And what phase they're in has really strong implications for the chemistry. So because of the sort of extreme physical conditions, you have really low temperatures and really low densities, the chemistry is obviously very different from how it plays out here on Earth. So in the gas phase, you only really build up chemical complexity through ion molecule reactions. And this leads to the formation of some really exotic and fun molecules like these large unsaturated carbon chains, but these are not really that useful if you're trying to jumpstart organic chemistry. Instead, we think that a lot of the organic chemical complexity originates from chemistry on the surface of dust grains. So you have submicron-sized dust particles, and the volatiles condense out onto these grains, forming an icy mantle. And within this icy mantle, you're able to get around some of these constraints on the chemistry and the energetics. And this is where you can efficiently form organic molecules. So as a word of jargon, in astrochemistry, we call anything that is 6 atoms or larger a complex molecule. This makes terrestrial chemists laugh a lot because it's not complex by any standards for Earth chemistry, but it is sort of the upper limits of what we can probe astronomically. All right, so the next piece that we have is we can also study the chemistry of both ices and gases along the entire star formation sequence. So we know that the birth of planets in solar systems is an outcome of the birth of low-mass stars. So this process begins in the molecular cloud. You have some overdensity of material, a perturbation that begins to cause part of the cloud to collapse in on itself. Oh no. Oh, there we go. Forming the young protostar. And the protostar sometimes has a young protostellar disk surrounding it, and it's still embedded in its parent envelope. Later on, the envelope will disperse, and you're left with just the dense disk of gas and solids in orbit around the star called the protoplanetary disk. And this is historically where we think that the planet formation process is really most efficient because you have high densities of solids in these really kind of flattened structures around the star. And then eventually everything that isn't incorporated into your planetesimals or planets is dispersed, and you're left with just your planetary system. So studying the chemistry along all of these different steps is actually really important for building up our understanding of how molecules are formed and also inherited prior to planet formation. So the last thing that I'll mention is the different tools that we have at our disposal to probe this chemistry. We have laboratory experiments, observations, and modeling, and these are really complementary. So with observations, we're able to get really direct constraints on the abundances and distributions of different molecules that we can observe, and we can also use molecules as tracers of the physical environment. We can use lab experiments to study the chemistry in a really controlled way, and this lets us get really strong constraints on the microphysics and the chemistry in these very exotic, sort of not Earth-like conditions. And then lastly, we can use models to make predictions for how the chemistry is going to play out in very complex environments. So this is especially useful for probing molecules that we can't actually observe directly, and sort of links the lab and observational approaches. So this tool, or this schematic is just sort of a guide for understanding some of the different approaches that I'll be talking about throughout the talk. So the idea is you can take one segment from each layer and combine them in different ways to approach different questions that you're trying to answer. So I'll be sort of coming back to this to help situate people throughout the talk. All right, so as a roadmap of where we're going with the science part of the talk, we're going to start by looking at how chemical complexity is built up in the earliest stages of star formation. We're then going to look at what actually survives the processes of disk formation and evolution. And then lastly, we're going to think about whether the disk itself plays any unique role in contributing to the chemistry and the chemical environment of planet formation. So let's jump into the first topic. So one of the sort of surprising developments in recent years is that complex molecules are now being routinely detected in the earliest stages of star formation. And this is actually kind of surprising because it's not obvious how you can build up this chemical complexity in very cold and energy-poor interstellar environments. So again, we think that this complex molecule formation is happening in the ice phase. And so to understand the formation of these complex molecules, we have to understand the microphysics and the chemistry within these ices. So we have important processes within the ices like accretion and desorption that populate the grain with different molecules from the gas. Within the ice, there's diffusion and reaction between molecules that can lead to the buildup of chemical complexity. And then there's also photoprocessing that can take place, either dissociating molecules, forming radical fragments that can then go on to react, or desorbing molecules back into the gas phase, also using photons. So understanding all of these different microphysical processes is really key to explaining how organics are forming in different interstellar environments. So like I said before, we can study these different microphysics in the lab in a very controlled way to get at some of these fundamental parameters. So we're talking about ice experiments. So this is the vacuum system that I worked on during my PhD. It's an ultra-high vacuum, so we get about 13 orders of magnitude below atmospheric pressure, and the temperatures are as low as about 10 Kelvin. So we can really mimic sort of space-like conditions. And we have a number of instruments in this chamber that let us study chemistry in the ice phase. So we basically, what does my pointer show? Yeah, so we basically cool a cesium iodide window down to very low temperatures. We release molecules into the chamber using this gas inlet, where they deposit onto the surface of this cold window, forming an astrophysical ice analog. And then we can use infrared spectroscopy and various energy sources to study how the chemistry is proceeding. And so the question coming back to this sort of how is chemical complexity built up in the early stages, we're really trying to understand the ice phase pathways that can lead to this production of organic complexity. Oh, thanks. All right, so I'm just going to talk about an example of a type of chemistry that we think is really promising for explaining the production of complex molecules in ices in very cold, sort of energy-starved environments. And this is chemistry that is driven by an excited oxygen atom. So it turns out that when you energetically process common oxygen-bearing molecules like CO2 or water, you produce an electronically excited oxygen singlet D atom. So in this example, in this example of CO2 dissociation at Lyman alpha wavelengths, we break the molecule apart into CO and then one of these O singlet D atoms. And this atom is kind of interesting because in the gas phase, we know that it has a very special property where it can actually insert directly into a carbon-hydrogen bond of something like methane and form an organic directly. And in the gas phase, we know that this chemistry proceeds with essentially no energy barrier, and you have a really favorable formation of your organic product. But in the gas phase, this molecule can't get rid of its excess energy, and so it typically actually fragments. So you're not building up organic complexity when this type of chemistry runs in the gas phase. So I was really interested in understanding what the energetics and products of this chemistry look like in the solid state. So you have to be a bit clever about setting up this type of experiment. We really wanted to isolate the chemistry coming just from oxygen atoms. And so to do so, we irradiate a mixture of methane and O2 ice, but we filter out wavelengths of light that can dissociate methane. So we can selectively dissociate the O2. And this leads to the production of these oxygen atoms, which then insert to form methanol, and we can monitor all of this within our experimental setup. So again, we want to answer this question of can this chemistry proceed in very cold environments? And to do so, we model the kinetics. So this is an infrared spectrum of methanol production over the course of an irradiation. And you can see on the bottom this growth curve of methanol and how much methanol is present in the ice over time in the experiment. So we can fit these growth curves to derive a reaction rate constant. We plot this at a given temperature, and the idea with this type of experiment is that if you have an energy barrier to the reaction, it should be proportional to the slope of the line on this plot. When we ran these experiments at multiple temperatures, we found actually a flat energy dependence, and so this is actually really exciting because it means that there's no barrier to this reaction. So consistent with what we were expecting from the gas phase, this chemistry should be active even in the very coldest interstellar environments because it has no reaction barrier. So we can, besides getting the energetics, we can also constrain the whole reaction mechanisms of how all of the molecules within our ice are related and the different branching ratios for different molecules that are produced as over the course of these experiments. And we can also test whether this type of chemistry is more broadly applicable. So it's nice that we can produce methanol, but we want to make even bigger, more complex molecules. So we also tested this oxygen atom reactivity with larger hydrocarbons and found that a really similar chemistry is at play. So this type of chemistry seems very promising. And when you compare to the protostellar ice spectra that were taken with Spitzer, you can see that a lot of the products that we can produce through this oxygen atom chemistry do show up in these interstellar ices. So it's great that this type of chemistry may be contributing to the production of these complex molecules early on in the star formation sequence. Okay, so we've thought a little bit about how we can actually generate organic complexity early on in the star formation sequence. And this is actually really important to understand because there's hints within our own solar system that chemistry from these early stages actually survived through to the planet-forming era. So among many other lines of evidence, you can see that there's a remarkable similarity in the organic compositions of comets within our own solar system and with the low-mass protostellar organic inventories. We also have evidence coming from isotope ratios and other kind of independent lines of evidence suggesting that at least in part there is some chemical inheritance from the earliest stages of star formation that was sort of delivered intact through to the formation of icy bodies in the solar system. So this brings us to the next stage of this talk, trying to think about what of this chemical complexity that's built up very early on actually survives the processes of disk formation and evolution. So first of all, is this inheritance conceptually plausible? If you think about a protoplanetary disk structure, we have these really strong gradients in the vertical direction because the surface of the disk is being strongly irradiated by the central star. And so in the surface, you have these really heavily processed, really hot, kind of UV exposed layers. But then once you get to the midplane, you're pretty well shielded from radiation. And so these environments are very cold and very well protected from radiation. So in principle, once you incorporate these interstellar ices into the midplane, we expect that they should indeed be well protected and preserved through to the planet-forming epoch. But the complication is that we know that disks are actually dynamic objects. So molecules or material that is incorporated into the midplane doesn't necessarily stay there. We have all sorts of processes like mixing, settling, and radial drift that redistribute material both vertically and radially through the disk and sort of complicate this picture. So what we're interested in understanding is whether interstellar ices can actually survive their journey through the disk given this dynamical context. So yeah, here in our little schematic, we're going to move on to models of ice chemistry in disks. All right, so this is work that I've done as part of my postdoc with Fred Chesla. And we basically take a physical model that describes the movement of individual dust particles within the disk as they're subject to processes like turbulence, vertical settling, and radial drift. So this is a single micron-sized particle that's initialized in the midplane, and you can see that it sort of wanders through all these different environments within the disk over the course of 1 million years. We couple this physical model with an ice model that mimics the protostellar structure and composition of ices. So protostellar ices, we know, begin with a very water-rich sort of core and have a thinner CO-rich layer capping that water-rich core. So we account for this structure, and then we subject these ices to destructive processes like thermal desorption, photodesorption, and photodissociation. So we start with these pristine ices and then basically see, as we subject them to these different processing mechanisms as the particle is journeying through the disk, do the ices survive at the end of their journey? So I'm just going to give a couple examples of how these simulations play out. So this is a micron-sized grain that's initialized at 20 AU. On the left, you're going to see that particle's actual trajectory in sort of Z over R space within the disk. And then in this left panel here, we're going to look at the UV flux that the particle is exposed to. And then here, we're going to look at the water and CO ice thicknesses that the particle sort of maintains. So we can see that it begins its journey in the midplane. It's not really being exposed to any UV here. But as it wanders further from the midplane, you get these big spikes of UV that it's exposed to. And that corresponds to these big drops in the column densities of water and CO within the ice. I should also mention the pink is sort of the parent molecule, and the orange is its photodissociation product. So as we dissociate water, we're forming initially just the dissociation product in the ice, and then eventually that too is lost, and the ice is basically bare. So for contrast, here's what happens to a micron-sized grain that's initialized at 150 AU. Out here, again, we're starting in the midplane, but the UV gradients are shallower in the outer disk. And so instead of this like really intense pulsing that we saw in the inner disk, we have a more gradual buildup of exposure to UV, which is never as intense as up here, but it's more consistent. And so you see this reflected in the ice compositions, where you have this more gradual sort of loss of the primary ice molecules. So I think the takeaway here is that when we couple physics and chemistry in this way, we see really different ice loss outcomes for different grains. And this is really primarily regulated by how efficiently a particle is transported into UV-exposed layers of the disk. So here's a summary of thousands of trajectories that we've run. Along left to right, we're looking at particles initialized at increasing disk radii. And then top to bottom, we're looking at different grain sizes from a micron to a millimeter. And the trends that I want you to take away are that as we go further out in the disk, we see more lofting of particles up to these UV exposed layers. But like I said before, the UV gradients are also shallower in the outer disk, and so the destruction that we see tends to be gentler in the outer disk. As the grains increase in size, we see less lofting away from the midplane. The particles become more sort of gravitationally bound to the midplane. But radial drift begins to take over, and once you reach a millimeter in size, the particle is really going to sort of efficiently spiral inwards towards the star. So with thousands of these trajectories, we can actually start to assemble some statistics for how ice loss proceeds in these disks. So here's a summary showing the ice loss outcomes. So we're looking at the fraction of the original ice mantle that's left intact after 100,000 years in these simulations for particles initialized at different disk radii and for different particle sizes. Okay, so the first thing to note is that small grains less than about 10 microns are really efficiently losing their ice mantles. So you can see these groups here are losing almost all of their ices. And this is also the sort of inner tens of AU of the disk is where we think that comet formation is taking place. On the other hand, larger grains, these 100 micron and millimeter size grains, are basically not losing any ice anywhere within the disk on the timescales that we're looking at. So the takeaway here is that it's actually very difficult to explain interstellar signatures in comets if comets form through the hierarchical assembly of local material. So you can't very easily start with these small particle sizes and preserve the interstellar material. Instead, what we think is a more plausible pathway to inheritance is to actually grow small particles into pebbles at larger radii in the disk and then drift this material inwards. So if you start with micron-sized grains in the outer disk, you're still only losing maybe 10% of your ice mantle. You can grow these to larger sizes, and then once they're a millimeter in size, they'll drift inwards, bringing this flux of interstellar material to the comet-forming zone. So this framework of pebble drift and pebble accretion as a way to explain planet formation is actually gaining a lot of steam in the planet formation community as a way to just explain sort of the fluxes of mass that you need to form planets and planetesimals. And so I think it's really exciting that using these chemical signatures, we have like a totally independent kind of support for this mechanism of planet and planetesimal formation. It's also worth noting that in this scenario where you're incorporating these interstellar ices into icy bodies in the outer disk, this really links the chemistry that we're seeing in the interstellar medium with potentially subsequent terrestrial chemistry. So icy bodies like asteroids and comets are thought to have delivered a lot of the volatiles here on Earth. And so if we're successfully incorporating these interstellar materials into these icy bodies, then there is sort of a direct link, perhaps, between the chemistry that's going on in the very early stages of star formation and then what's ultimately happening on planetary surfaces. Okay, so we've seen that we can build up chemical complexity early in the star formation sequence. We know that to some extent we can preserve this material through the formation of icy bodies in the solar system. And so now we're going to come to this question of what is the role of chemical reprocessing within the disk. And for this section, we're mainly going to be using gas phase observations of disk chemistry. All right, so the ability to study complex chemistry in disks is actually pretty recent. So the first detection of complex organics in disks was made just a few years ago. Methyl cyanide was detected first in 2015, followed by methanol in 2016, and these are both done thanks to the ALMA array, which I know several people in this department use. So we're really just beginning to understand the complex chemistry in disks, and really fundamental questions like, are these complex organics common or rare in disks? Are they inherited from the early stages or formed through disk chemistry? And are they important or minor species as far as the total volatile budget goes? So we set out to address some of these questions, and in particular, looking at the chemistry of these complex nitriles, methyl cyanide and cyanoacetylene in discs. So jumping right into the detections, we found that methyl cyanide is firmly detected in 3 of the 6 discs in our sample, with 2 additional sort of tentative detections here and here. And cyanoacetylene was detected firmly in 5 of the 6 discs in the sample. So it's really cool that now that we actually have the sensitivity to go looking for these complex nitriles, we see that they're showing up fairly commonly. So we can do more than just sort of say that they're common. We can actually quantify how important these complex species are as carriers of the nitrile bond. So to do this, we use a disk physical model where we set the temperature and density based on other observations, and then we just do a parametric abundance retrieval, and we can get really nice matches between our observations and the modeled images. So the result is that we have now these ratios of the complex nitrile, methyl cyanide, or cyanoacetylene with respect to HCN, which is a simple nitrile carrier. And these are the abundance profiles as a function of radius in the disk. So what we're seeing is that in the inner 100 AU of the disk, methyl cyanide accounts for about 1 to 10% with respect to HCN, and cyanoacetylene is 1 up to even sort of as abundant as HCN within the disk. So this is telling us that these complex nitriles are actually important carriers of the nitrile bond at the radii in the disk where comets and planets are forming. So if we want to understand sort of the total inventory of volatiles and the delivery of these different kind of volatile groups to planet-forming material, we do have to consider the chemistry of this more complex material. All right, so how does this nitrile chemistry in disks compare to other stages of star formation? So here I'm showing the ratio of methyl cyanide with respect to methanol, which is just the oxygen-bearing analog, basically, of methanol. And in only 1 disk has methanol actually been firmly detected, that's TW Hydra, and in that disk the ratio of these molecules is about 1. And there's 2 other disks where we have pretty strong upper limits for methanol, so we can make lower limits that are also consistent with about 1 for this ratio. And when we look at how this compares to earlier stages of star formation, we see this huge leap in the methyl cyanide to methanol ratio. So between the protostellar and hot Carino phase, the disk phase, we have about 2 orders of magnitude higher methyl cyanide to methanol ratio. So this is kind of a dramatic change in the chemistry that's happening in these disks. Now, there's a really compelling explanation for why we are seeing this trend, and it actually has to do with how the physical evolution of the disk is coupled to the chemical evolution. So the idea is that in a young disk, you have these small grains that are really evenly distributed throughout the vertical extent of the disk. And these small grains are coated in ices. And as grain growth and settling proceeds, these ice-coated particles grow and settle to the midplane and bring their volatile reservoir with them. So you end up with a midplane that's very rich in water ice. You've sort of trapped your volatiles in larger bodies in the midplane. And consequently, you have an atmosphere that's very depleted in gas phase oxygen. So you're sequestering oxygen from the surface of the disk into the midplane. And in this oxygen-poor gas, you promote a really reducing chemistry. So this means that you're going to really efficiently produce molecules like nitriles and hydrocarbons in this very oxygen-depleted gas. And so qualitatively, this can explain why we see these unusually high abundances of methyl cyanide in these mature disks. So until very recently, this was very much just a qualitative explanation for a lot of the trends that we were seeing in disks. But we set out to try to understand whether this oxygen-depleted gas framework can actually systematically explain the emission of nitriles and hydrocarbons that we're observing in disks. So to do so, we set out to survey what is in disk studies a statistical sample of 14. looking at the hydrocarbon, nitrile, and oxygen chemistry in 14 disks spanning from about 1 million years to 10 million years in age. So this is just a gallery of a subset of the disk sample looking at C2H, HCN, and CO, again, are tracers of hydrocarbon, nitrile, and oxygen chemistry in these disks. And they're really beautiful. You can see the sort of diversity of emission that we see both molecule to molecule and disk to disk. And this diversity is speaking to the fact that you have very different chemical outcomes in the different physical environments of each of these disks. So we can use these sort of statistical surveys to try to understand what's actually driving these chemical sort of differentiation outcomes that we're seeing. So we were able to derive abundances of C2H and HCN towards our disk sample. And really excitingly, we saw that there's actually a positive correlation in the abundances of these molecules. So consistent with our expectation from this oxygen poor chemistry framework, it seems like the nitriles and the hydrocarbons are forming from a shared chemistry consistent with an oxygen depleted gas, where you really have just sources that are efficiently forming nitriles are also efficiently forming hydrocarbons. Yeah, so just with these more statistical samples, we can actually start to test the underlying mechanisms for the patterns that we're seeing in these disk chemistry observations. Now, let's take a step back and think about the importance of this for of observing these nitriles. It turns out that in many prebiotic chemical frameworks, nitriles are actually sort of keystones in the chemical synthesis of larger organic molecules like amino acids, nucleic acids, and so forth. So the fact that in the protoplanetary disk stage, we seem to be sort of uniquely producing both simple and complex nitriles really speaks to that maybe the disk stage is playing a really important role in producing these prebiotically important nitriles that may seed sort of subsequent chemistry on planets. All right, so this sort of begs the question then, when does this sort of unique oxygen poor chemistry actually begin within these disks? This is especially important in light of growing evidence that planet formation is actually already underway in the embedded stage. So, like I said at the beginning, historically we've really looked at protoplanetary disks as the main sites of planet formation, but with ALMA we can now see, even in sources that are still embedded in their parent envelope, these really dramatic ringed structures that are suggestive of at least the initial stages of grain growth and dust processing. So we really have to sort of reconcile now our understanding of planet formation chemistry and understand, are these trends that we're seeing in the more mature disks also at play in these younger disks where the early stages of grain growth and planet formation are underway? So this type of observation has been really challenging to do because protostellar disks are still embedded in the envelope. But again, thanks to ALMA, we're getting better at making these measurements. So this is part of an ALMA survey of 5 protostellar disk candidates, all sort of less than 1 million years old. Here I'm just showing a couple of molecules towards 3 of them. But you can see that with high resolution and being a little bit clever about what velocities you're looking at, you can actually pick up rotation signatures in the protostellar cores. So we're getting much better at isolating these coherent velocity structures that correspond to emission from either the protostellar disk itself or the disk forming region. All right, so coming back to this question of trying to understand when the disk gas is becoming oxygen poor, we can use CO as a sort of proxy for the oxygen content in the gas. And so here I'm showing the CO abundance for many different protostellar and more mature protoplanetary disks, where these embedded disks that I just showed you are on the younger end and the more mature disks are on the older end. And so what we're really trying to understand is when in the disk lifetime does this oxygen depletion or CO depletion show up? So it's a bit of a hard measurement to make because even the rare isotopolog C18O can be optically thick, but we can use a more conservative benchmark to account for this. And so looking at this sort of blue line, we see that the very youngest protostellar disks still have a CO abundance that's consistent with interstellar. So oxygen is not depleted in these earliest protostellar disks. But by the time we get to 500,000 years or so, it's really difficult to reconcile these low abundances with an interstellar value. It seems like they must be at least sort of an order of magnitude depleted in CO. And so this is giving us some constraints on the time scale for this oxygen depletion, that it's happening maybe between 500,000 and 1 million years within the disk lifetime. So again, this oxygen poor gas, or the reducing chemistry that we see in more mature disks, is probably established pretty early in the disk lifetime, maybe around or just before the disks enter the class 2 stage. All right, so I want to just say a word about what I think is some really exciting sort of new frontiers in our ability to study disk chemistry. So this is a gratuitous comparison of what ALMA can do compared to even earlier ALMA and SMA. So this is the same molecule in the same disk, and you can see what the image looks like at low resolution, at moderate resolution with ALMA, and at the highest resolution that ALMA can achieve. And you can see that with these sort of state-of-the-art observations, we now have really exquisite detail that we can pick up in the molecular emission patterns within these disks. So this far right image is taken as part of the ALMA large program MAPS, which is led by Karen Oberg. And it's for those of you familiar with D-sharp, it's basically the D-sharp of chemistry. So we're looking at 5 disks at 0.15 arcsecond resolution in a whole suite of different molecular lines. And what's really exciting about this type of high resolution observations is that they can actually probe spatial scales that are directly relevant for planet formation. So a lot of the trends that I've been talking about up until now have been based on these sort of moderate resolution observations that are probing further out in the disk than where planets are actually forming. But we're now zooming into the spatial scales that are more relevant to planet formation, and so this is a really exciting direction going forward. So I'm not going to talk too much about this, but just to give sort of a snapshot, within the MAPS collaboration, I was working on observations of the CN molecule, which is the simplest nitrile. So this is what CN looks like towards the 5 disks in the MAP sample. You can see also a lot of heterogeneity in the emission patterns here. And what's really cool about working with these high-resolution chemistry observations is we can start to actually see real trends in how the nitrile chemistry is varying across the disk. So what we're looking at here is the CN to HCN ratio as a function of radius in the disk. And even among the nitriles, these simple nitriles, we're seeing maybe 2 orders of magnitude variation in the CN to HCN ratio across the disk. So I won't go into too much detail here, but really we can use these constraints to actually infer what physics are driving the production of nitriles within the disk. And again, we're very interested in this from the standpoint of better understanding how these prebiotically interesting molecules are produced. All right, so we've spent a lot of time talking about carbon, nitrogen, and oxygen up until now. And that's for the very practical reason that it's really easy to detect carriers of these elements at all stages of star and planet formation. It's a really different story for phosphorus. There's only been 2 detections of phosphorus towards any low mass star forming region up until now. So I want to spend a few minutes talking about some progress that we're making, better understanding sort of the most elusive of these biogenic elements. So to study phosphorus, we actually have to go back to the protostellar stage. It's never been seen in a disk. But in 2019, we detected PO and PN towards the B1A protostar as part of a different survey of molecular lines towards protostars. We ended up with these really nice detections of PN and PO that were made with the IRM 30-meter telescope. So this was sort of exciting in and of itself, because again, it was just the second time that these molecules had been detected in a sort of sun-like star-forming region. But what's really exciting is underway, we have follow-up observations that have been delivered by ALMA. And so now, instead of just a little spectrum, we have both spectral and spatial constraints on where the phosphorus is emitting from. So you can see the white contours here are the continuums. So we have a sort of disky-like structure within this protostar. And the PO and PN are emitting from these 2 distinct clumps that are pretty offset from the dust continuum. And we also see some really interesting differentiation in the emission patterns of these two phosphorus carriers. All right, so we can use these emission maps to try to understand better how phosphorus is actually stored in the dense interstellar medium and why it's so hard for us to detect. So the first thing we want to do is compare the phosphorus emission to other line tracers, things that we know trace different protostellar environments. So phosphorus has been pretty consistently linked to the presence of outflows. So it's been thought that phosphorus would emit from within the outflow where you have shocking and sputtering of the actual refractory material. But what we can see here is SiO tracing the really high velocity shocks within the outflow doesn't actually emit co-spatially with the phosphorus molecules. They're sort of offset from the SiO outflow. What's really cool is that they actually do seem to be localized to regions in the protostar where the SiO outflow is interacting with this dense filament of gas that we trace with CCS. So it seems like we have some shocking of more pristine interstellar material, this sort of dense clump that's actually releasing phosphorus into the gas. It's not coming from the outflow itself. We can also look at how the emission of these phosphorus molecules compares to other low velocity shock tracers. So here we're looking at SO2 and methanol compared to the PN emission. And these are molecules that are more connected to the sputtering of icy material rather than the sputtering of grain material. And we see a much closer correspondence here. That being said, phosphorus has never been detected towards a hot core or a region where you would have thermal sublimation. And so it seems like the phosphorus molecules cannot be as volatile as these simple ice carriers. So we can use these trends to try to say something about how phosphorus is stored in the grain. So this is just a comparison of different sort of proposed phases that phosphorus might be stored in. And you can see that the metal phases of phosphorus, like schreibersite for instance, have a volatility that's really similar to silicate. And so we think that actually this isn't a good candidate for what's storing phosphorus in the grain, because then we should see a much more similar morphology to the SiO emission. So instead, something like phosphorus oxides or mineral phosphates fit really nicely with this trend of intermediate volatility between simple things like water and very refractory things like silicates. Of course, nobody likes N=2 science, so we've also been devoting some effort to detecting phosphorus towards more low-mass star-forming regions. So we led a fishing expedition with the 30-meter telescope looking for PO and PN in 7 low-mass sources that have really well-characterized outflows. And this is work that I'm working with an undergrad at Harvard who's actually doing the analysis on this. We have 3 new detections of phosphorus molecules towards low-mass star-forming regions. So just by looking in the right places, we've actually over doubled the sample size of phosphorus emitting regions in sun-like star-forming regions. And as our sample size continues to increase, we can start to constrain better how and when phosphorus is released into the gas and to understand its chemistry a little bit better. So it's, basically we're finding that there's no correlation in the detection of phosphorus molecules with any source physical properties like the age or the luminosity. So we see PN detected at very early ages and very late ages, so no real trend here. Basically, the only sort of loose correlation that we could find is that the sources where phosphorus molecules were detected all have high fluxes of water. And this is a proxy for outflow shocking within low-mass star-forming regions. So again, it's sort of consistent with this picture that outflow shocking is playing a role in releasing phosphorus into the gas. But I think we do really need resolved observations of these new sources to better understand the particularities of their chemistry in these regions. All right, so just to come back to our original roadmap, we started by talking about how chemical complexity is built up in the early stages of star formation. We can use these lab experiments to really constrain the ice microphysics and to gain some insight into these questions. We then talked about how this chemical complexity that's built up very early can survive the formation and evolution of disks. And we showed that there are signatures both in our observations as well as the sort of simulations that we can produce that indicate that this type of inheritance is indeed plausible. And then we finally talked about the sort of unique role that more mature protoplanetary disks play in generating these prebiotically interesting nitriles because of the coupling between the physical and chemical evolution of the disk. So with that, I will just sort of summarize that by synthesizing all of these different approaches, we can really assemble a more complete picture of how these different biogenic elements are behaving throughout the star and planet formation sequence, and say something about the inheritance of these ingredients in planet forming systems. So happy to take any questions.
Great talk, first of all. This might be a dumb question, but could you maybe just go over again the time scales that we're talking about here of, like, I remember back in Emery's exoplanet formation course a few years ago, we learned about the millimeter barrier and drift and all that stuff, and I'm wondering how the time scale of these gradients drifting inward compares to the time scales of how they grow and how the volatiles are processed. Like, obviously, there's going to be some growth as they're drifting.
Yeah, great question. So that's actually sort of what set the time scale that we looked at was the time scale of growth. So the particles obviously behave differently depending what size they are. So we limited our simulations to 100,000 years because it seems like about the upper limit that a particle will remain at a given size before its dynamics will be really altered through growth. So that's what set that. But you're definitely right, like the radial drift that I was talking about is basically one of the problems contributing to the meter barrier. And so that's kind of one of the nice things about this pebble accretion model is it takes what used to be a problem in planet formation and turns it into a solution. It says take all this flux of pebbles from the outer disk and use it to contribute to the mass of forming planets. But there's also other solutions like pressure structures in the disk and so forth that can trap material and give you a little more time to form planets. Yeah.
I'm curious about the timing of selecting dust sizes to worry about. So what is it about your 1 micron dust that makes it with
Yeah, so that was based on, we think that interstellar dust grains are at most about a micron in size. So it was sort of just the starting point for grain growth, assuming that you're starting with an interstellar-like dust and growing up to a few orders of magnitude higher, these millimeter pebbles that behave really differently. Yeah, exactly. The chemistry, I mean, molecules are like a lot smaller than dust grains, so they should be pretty agnostic of the size of the particle that they're on. Yeah. So there's some like recent discussion of whether surface tension is higher in the smaller grains, and that can explain different desorption properties of different volatiles, but I don't think it's a first order effect. Mm-hmm.
You should probably repeat the question so they get recorded.
Oh, yeah. Whoops.
And there's also a couple of items on chat.
Oh, yeah.
I can search those.
Okay.
I've got a question here.
So I'm really curious about this idea of, planet formation process starting in the protostellar disk phase.
Yeah.
Because for high energy radiation in the disk picture, it's always been like, you don't have to care because everything's in the midplane.
Mm-hmm.
So I'm wondering, is there any persistence of information for like, in this protostellar disk phase where you are exposed to a bunch of high energy radiation? Does any memory of that survive the planet formation process through to the planetesimal stage?
That's a great question, and it's not understood yet. There's a lot of talk within the meteoritic community that the formation of like these very refractory inclusions that were formed by melting probably correspond to like outbursts in the protostellar stage. So there's some circumstantial connections, but it's still quite hard for us to actually probe the relevant spatial scales within the protostellar disk. So hopefully we'll have some better constraints. But the other thing is that you have an envelope still in the embedded stage, and that actually blocks a lot of the disk from experiencing much radiation at all. So you'll have really heavy processing in exposed regions like the outflows, but the disk itself is actually pretty well shielded still.
There's a couple of these on here. Yeah, maybe pick one, and then we'll probably have to wrap up.
Okay.
Whichever you think is most interesting. Or the easiest to answer.
Okay. Well, the shortest one. Oh yeah, you guys can see these too. Okay, so I don't have to read it out loud again. The oxygen is depleted in middle-aged disk. So it's still a question of where exactly the oxygen is stored. It seems like it's not globally depleted, but sort of repartitioned from the surface of the disk into the midplane, where it's probably stored in maybe larger oxygen-bearing organics, or somehow in just sequestered like physically by the growth of grains. But it's not that we're losing it from the whole column, it's just being redistributed into the midplane.
Okay, one last one.
Oh, that's right. It's a really excellent talk. I just had a question about the bearing of this on the formation of planets and moons in our own solar system.
Mm-hmm.
Specifically, the question of whether Saturn's moon Titan has a primordial atmosphere versus secondary atmosphere is a big question in planetary science. It seems like this process of depleting the atmosphere in oxygen species and creating a reducing environment might be similar. So I guess my question is, along the lines of the timescale arguments, is it possible that something similar was going on in the Saturnian subnebula, or is this exclusively in the disk during evolution?
Yeah, that's a great question. So it seems like photochemistry is an important part of why this depletion happens, actually. And so I'm not sure if the Saturnian disk is only in the sort of the midplane of the protoplanetary disk and it's not being exposed to UV, whether this sort of partitioning would happen in the same way. But that's a really interesting question to think about. I don't know that much about Saturn, but we should talk more about it.
Awesome. Thank you for coming. Let's give Jenny a hand for a great talk.